Hello, I'm Branden, and I like to write code that doesn't compile. Unlike the intern who somehow managed to circumvent your team's CI pipeline, I do it on purpose. I've been programming for longer than the median college student has been alive, and in that time I've acquired the attitude that what I want is software that can't not work. This talk's inspiration comes from my experience striving for that goal. It addresses a particular set of circumstances. And due to this, if you exclusively work on programs that are only used once, never read by another human, and then permanently deleted from every computer, you are outside the target audience. Raise your hand if that's you. Yeah, I figured. While I'm at it, I do want to stress that this talk isn't academic. I'm going to describe some advanced techniques that require judgment on when to apply them, but they've all been used in real systems, and I've watched them actively save hours of developer time. And lose developer time, but I'll have advice about that. I'll start off with something a bit more universal, though. There's a good chance you've seen something a lot like this. I have an interface type and a type that implements that interface, and then I have this blank where I assign the concrete type to a variable declared with the interface type. This code does nothing. No matter what else I write, if the program compiles, there's no way to use or even observe the assignment. This code doesn't compile. The compile time error that I love tells me that the type doesn't, implement the interface, along with why it doesn't. Go doesn't have an implements keyword, but this serves kind of the same purpose. We might call it an implements assertion. Even though we would normally get the same error message wherever we try to use Bochi as a guitarist, this lets us have the error point right next to the type. That's especially nice when the interface, implementers, and usage are all distant from each other, a la dependency injection, and especially if you're still prototyping a design such that the interface might be subject to change. When you adjust the interface's methods, having a lovely compile time error to take you right to the place to make changes can end up saving a lot of time. This implements assertion can be thought of as the programmer making a claim. Bochi is assignable to guitarist, and having the compiler verify that claim. Compiled Go programs are therefore evidence of the correctness of all the claims in their source code. The question arises, what other kinds of claims can we make? That's surprisingly tricky to answer. Generally speaking, we need to work within the list of things that the compiler computes, and Go makes a point of limiting that list in order to have fast builds. However, every Go compiler does arithmetic on numeric constants. We can do an assertion by putting the arithmetic somewhere that only a particular value makes sense. There are a few candidates for this, but the strongest is in the size of an array. And to be clear, this has nothing to do with slices. Have the compiler compute some constant, subtract out what I expect the result to be, and I have an array that's size 0 if and only if I'm correct. We do need to use constants exclusively, which means there aren't a lot of things we can put in there. The first thing is probably obvious. It turns out that constants are constants. If I use iota to define a list of them, I can assert any of their values using this technique. I can't blame you if that doesn't sound particularly useful, but it turns out that if you've ever used the stringer tool, you've used this, or technically a closely related thing. I would love to go into the details about what's different, but this segment is called lightning talks for a reason. Thanks to this generated code, the string method for this type can never drift out of sync with the actual list of constants. If you rearrange them, remove them, otherwise change their values, a compile time error reminds you to rerun stringer. I love compile time errors. Other than name constants, there's another category that we can use to bring into these checks, and that's built-in functions. There are some which more or less take types as arguments and return constants. For example, len and cap give constants when their arguments are array types, although I haven't actually found a use for those in particular. Ironically, the built-in functions I've used most for this purpose live in package unsafe. Size of, align of, and offset of effectively take types, even if they aren't written as such, and they produce integer constants. Therefore, we can use them in that numeric assertion pattern, and if we don't immediately know the number to use, the beloved compile time error will guide us there. Start with 0 as the assumption, as I've done here, and the compiler will tell us we have a value of type, in this case, 16 struct. That means a Bochi is 16 bytes. Toss in that number, now it compiles. But let me remind you that this talk is about detecting incorrect programs without having to run tests. Raise your hand if you've ever compiled Go code for ARM, like a Raspberry Pi. Decent number. There are details of type layouts that differ between target platforms. My assertion doesn't pass on ARM, so the code doesn't compile. Eric and Johnny have been offering trivia questions this week, and I have one of my own. Is the size of this type 12 or 16 on WebAssembly? I'll give you 2 seconds to answer. 16 is correct. It's possible to get this assertion to work everywhere by very explicitly saying what you mean instead of summarizing. Realistically, the better advice is to only use this technique where it matters. Like if you are writing a high-performance data structure, for example, a Swiss table implementation for the Go runtime, and your type has to be exactly aligned with cache lines to avoid a performance glyph. Or where the types are outside your control, and you need a reminder to update code and tests when they change. I've used this guarantee that to guarantee that my choice of Go type for a CGO-free API wrapper was a correct one, as well as during prototyping when a type was generated from someone else's database schema, so that I would always have a reminder to update unit tests when new columns were added. It's also nice if you need an unsafe copy of a type defined elsewhere to work around a critical performance issue. Unfortunately, this is how the Xtools folks recently learned not to put this kind of check in importable code. If your assertion fails due to a change somewhere else, everyone who imports you stops compiling as well. Test files are great for this. Now, I've had to talk pretty fast to get out everything I want to say, and there's still plenty more that I could add. That said, it's the themes and the mindset of this talk that are really important. Writing, or whether you're writing static assertions like I've shown, or just designing an API that's hard to misuse, making code that can't not work saves hours each time. So my task for all of you is to turn investing in your code into the next business catchphrase. I have a picture of a cat sitting on me. Thank you.